This last learning video for Unit 5A summarizes the mineral groups. And mineral groups are based on composition. So really all you have to do is look at the chemical formula and you'll have an idea of what mineral group a mineral belongs to. Here's a pie chart showing the most common minerals on Earth's surface. And I know that you're just learning the names, but the plagioclase feldspar all the way around to the mica, this entire region here, these are all silicate minerals. And they're silicate minerals that form during igneous processes. So when we talk about igneous rocks, we'll be talking about all of these minerals. Clay is also a silicate mineral, but it forms from weathering and sedimentary related processes. Other silicates are listed here. So really, 92% of the minerals on Earth's surface are silicates, and only a small 8% are non-silicates. Many of these are formed during sedimentary processes such as evaporation, which can form huge halite deposits, which is rock salt, or gypsum deposits. So when we talk about sedimentary rocks, we'll talk more about non-silicates. Another important group of non-silicates are ore minerals. We'll talk about ore minerals near the end of the semester. Here's the elemental abundance in continental crust. So these are the elements that are most abundant. And I'm not expecting you to memorize these, but I would like you to pay attention to these first two, oxygen and silicon, because these make up the silicate minerals, which is why they're so abundant. Now, when you think of oxygen, you probably think of air, but you shouldn't think of air in this particular case. This is oxygen that is a solid. It's bound to other atoms and it forms a solid like a mineral. So if you think of ice, H2O, there's O in there, but it's frozen, right? It's a solid. So don't think of this oxygen as atmosphere. So the two mineral groups, as I've just alluded, are silicates and non-silicates. So we'll start by looking at the silicate group. As I mentioned, these are the most important mineral group when it comes to rock-forming minerals. And the reason they're so abundant is because there's so much silicon and oxygen in the Earth's crust, like I just showed you. The fundamental building block of silicate minerals is the silicon-oxygen tetrahedron. And I sort of think of it as a Lego piece that you can take as a fundamental unit, and then you can arrange it in different kinds of chains or sheets or three-dimensional structures. So that fundamental Lego, that fundamental unit, is the silicon-oxygen tetrahedra. It consists of 4 oxygen ions and a much smaller silicon ion. Remember, ions have charges. So here we have a picture of a tetrahedron with a silicate ion in the middle and then 4 oxygens attached to it. Let's take a quick look at the electron structure around these two elements. Silicon is element 14, which means it has 14 protons, and a neutral atom of silicon has 14 electrons. Remember our rules that we can only put 2 electrons in the first shell, and then we can put 8, and then we can put up to 8 more in the next shell. Well, because we only have 14, we have 2 and 8, and then 4 in this outer shell. And remember, this outer shell will be full if it has 8, or if we get rid of these 4, and then we have 8 in this shell. Oxygen is element 8, and so it has 8 protons, 8 electrons. The first 2 electrons go in the inner shell, and then we have 6 electrons in the next shell. Again, 8 is stable. So what happens when these two elements combine is that silicon donates its 4 electrons to 4 oxygen atoms. And because of that, it winds up with 4 missing negative charges, and it becomes a silicon ion with a +4 charge. Oxygen, on the other hand, takes an electron from 2 different silicon atoms, because it's attached to 2, and that gives it a net -2 charge. And so oxygen is shown as a -2 ion. So here we are back to our same picture. We've got the +4 silicon ion in the middle, 4 -2 oxygen ions around, and so the overall net charge is -4, right? Because we have -2, 4, 6, 8. We've got -8, +4. the net difference is -4. So this SiO4 silicate ion needs to combine with something that's preferably a positive ion to form a stable compound. One way that this can be arranged is in this structure called the quartz structure. Quartz is SiO2. So in that case, every silicon ion is sharing 2 oxygen ions. But tetrahedra can be arranged in other ways. Over here we have single tetrahedra, where the tetrahedra are by themselves, and there are other elements involved, but the tetrahedra remain isolated. They're not chained together. Here we have a chaining of tetrahedra. This is called a single chain. There's some oxygens here that are being shared by the tetrahedra. Here we can hook our Legos together in an even more complex way, and we can make a double chain. Not only are the tetrahedra sharing an oxygen in the given chain, but then between them they're also sharing an oxygen. We can go further and make an entire two-dimensional sheet. This is like the Micas that have a very strong sheet structure. Finally, we can move on to a three-dimensional framework structure. This is the structure of feldspars and also similar to the quartz structure that I just showed you. So those are the structures of the silicate minerals, and we will definitely come back to them again as we look at rocks. Many of the non-silicate minerals, which do not have silicon in them, are important economic minerals. And as I mentioned earlier, they only comprise about 8% of the Earth's crust, and they're often in sedimentary rock units. Some examples of non-silicates that are important include hematite, which is mined for iron, sphalerite, which is mined for zinc, galena, which is mined for lead, and copper is mined for copper. Here's a chart showing the common non-silicate mineral groups. And the main thing I want to show you here is how these mineral groups are organized. So the silicates have silicon in them. The oxides have oxygen in them without any silicon or any other negative ion. The sulfides and sulfates have sulfur. The sulfides have a single sulfur, and the sulfates have an SO4 in their structure. Native elements are elements that are made of a single element. So we have gold, copper, diamond, sulfur, graphite, silver, platinum. These are all native elements. The halides are made from elements in the 7th column of the periodic table called the halides. Chlorine and fluorine are part of that column. The carbonates have CO3 in their formula. So this is the way that each of these is distinguished. The names of some common minerals are here, as well as their economic use. Many of these minerals are important ore minerals that are used in industry. I'd like you to pause the video now and try pages 47 and 48 in your lecture tutorial notebook. Okay, here we go. So the first part asks you to examine the chemical formulas of these various minerals and decide the mineral group. If it's a silicate, then it's going to have silicate and oxygen. And there are 2 silicates listed here that I want to bring your attention to now because they're going to be very important when we talk about igneous rocks. There are silicates that are iron-free. They have no iron, no magnesium, and they're light in color. They're called felsic. Feldspar, silica, that's kind of the derivation of that word. Then there are silicates that have iron and possibly magnesium. These tend to be dark colored and they're called mafic for magnesium, ferric iron. So those are 2 words I'm introducing now. We're going to come back to them when we talk about igneous rocks. If we see carbon and oxygen in the chemical formula, then it's going to be a carbonate. And carbonates often fizz with hydrochloric acid, such as calcite. Other groups, we're only having these 3 groups here, silicates, carbonates, or other, do not have silicon, and they don't have carbon and oxygen. So let's get started. The first one is quartz, and it's SiO2. It has silicon in it and oxygen, and that's it. So it's an iron-free silicate. It doesn't have any iron in its chemical formula. Just as a reminder, that means it's felsic. Then we have potassium feldspar, which also has silicon and oxygen, but again, no iron, no magnesium, so once again, a felsic iron-free silicate. We then have calcite. You'll notice calcite does not have silicon in it. It has carbon and oxygen, so this makes it a carbonate mineral. Biotite has silicon in it. It also has oxygen, iron, and magnesium. So biotite is not an iron-free silicate, it's an iron-rich silicate, and we call it mafic. Finally, we have pyrite. Pyrite has iron in it and sulfur, and so it's not a silicate, but it's other. Two groups of students are debating the classification of graphite. One student thinks graphite belongs to the other category, and the other thinks it's a carbonate. But student one is correct. For a mineral to be a carbonate, it must have carbon and oxygen. Graphite is actually classified as a native element since it's made of only one element, carbon. Explain why hematite is not an iron-rich silicate mineral by using the key elements in the formula. Well, we have iron and oxygen, but we don't have silicon. And if we don't have silicon, it's not a silicate mineral. An igneous rock called gabbro is made up of a lot of iron-rich silicate minerals. So what color do you think it's going to be? Well, iron-rich silicate minerals are dark-colored, so a gabbro is also a dark-colored rock. Then we have the two micas, Muscovite mica and Biotite mica. Their formulas are kind of long and very similar. However, they're not exactly the same, so it asks you to differentiate them. So first of all, they're definitely silicates because they have silicon in their structure. But biotite has iron and magnesium, so it's going to be a dark-colored silicate. Muscovite does not have any iron or magnesium, so it's going to be a light-colored silicate. Here is biotite, which is very dark, and muscovite, which is very light. We're done with our introduction to minerals, mineral properties, and mineral compositions. Coming up next, we're going to talk about minerals and economics.